In section 3.1, we graphed higher order polynomials. We had already known how to graph linear equations and quadratic equations, but in 3.1 we extended that to 4th, 5th, 10th, or 15th degree polynomial equations. But we could only get an accurate graph. We could only find the x-intercepts if the function was given to us in factored form. So in 3.2, we learned how to use synthetic division to determine if a given number was a zero of a polynomial, or if a given factor was a factor of a polynomial. In section 3.3, we're going to talk a little bit more about zeros of polynomials, and then in 3.4, we will learn how to find zeros of a polynomial even if it's not given to us in factored form. All right, section 3.3, zeros of polynomials. The first thing that we need to do in this section is talk about how to find a polynomial with given zeros. Now, one thing that you may want to remember that was on the 3.1 notes was the note about multiplicity of a zero. If a zero had odd multiplicity, we said the graph crossed the x-axis at that zero. So it was either coming up from below and crossed, or it was coming down from above and crossed. If C was a zero with even multiplicity, then we said the graph does a U-turn at C. It's either coming down, touches the x-axis at C, and then turns around and goes back up, or it's approaching the x-axis from below, hits C as an intercept, and then turns and goes back down. That will help us interpret graphs that we're going to be given on a couple of those problems and help us find the polynomial that matches the graph. All right, let's do a few examples. The first few problems say, find a polynomial f of x of degree 3 that has the indicated zeros and satisfies the given conditions. So we're going to be given zeros of the function, we're going to be given some other information about the function, and we're looking for the polynomial that satisfies those conditions. We did something similar to this with quadratic equations. We said that if, let's see, in the 11th edition, this is page 237, and we said that if these are zeros of a function, then we know 3 factors of the function. If negative 5 is a zero, then x plus 5 has to be a factor. If 2 is a zero, then x minus 2 has to be a factor. And if 4 is a zero of the function, then x minus 4 has to be a factor. So already we have a 3rd degree polynomial that has the 3 zeros, negative 5, 2, and 4. But how do we make this 3rd condition true? I suspect that if we just let all the x's be 0 here, we probably wouldn't come up with y equals negative 24. So what we need to account for is some unknown coefficient. Given that f of 3 is negative 24, that means if I put 3 in place of all these x's, then y will be negative 24. And that's everything I need to solve for this coefficient a. That right-hand side would simplify to 8 times 1 is 8, times negative 1 is negative 8. So negative 8a equals negative 24. That means the coefficient that we need to satisfy that last condition is 3. If we let x be 3, not x, if we let a be 3, Then we have the specific polynomial function 3 times x plus 5 times x minus 2 times x minus 4. And we can just look at it and see that sure enough, the zeros are -5, 2, and 4, like we're specified. And we can double check if we let x be 3, we should get y as 24. Let's check that real quickly. If we let x be 3, this would be 3 times 8 is 24. 3 minus 2 is 1. 24 times 1 still 24. 3 minus 4 is -1. And this 24 times -1, sure enough, is the -24 that we were supposed to get. Now, in the answer in the back of the book, they have probably multiplied that out and written it in standard form, and that's okay. I'm not going to ask you to do that on the test because it's time consuming. If you just leave that in factored form, that's fine. All right. Let's do one more example that has a little bit different twist to it. Notice that in number 6, we're given 2 imaginary zeros and 1 real zero. Can we come up with the polynomial function that has these 2 imaginary zeros, this real zero, and also satisfies the condition f of -1 equals 50? I'm not sure how that's going to work, but we can start it the same as we started number 2. We can just say if -3i is a 0, then x minus 3i is a factor. If positive 3i is a 0, then x plus 3i is a factor. And I actually said those backwards. If -3i is a factor, then x plus, let me try one more time. If -3i is a 0, then x plus 3i is a factor. If positive 3i is a 0, then x minus 3i is a factor. And if 4 is a 0, then x minus 4 is a factor. And then we're given the one other condition, f of -1 equals 50. So we'll have to find some coefficient a such that if we let all of these x's be -1, we'll get a y value of 50. I'm going to put 50 in place of y, or f of x. I'm going to actually, I just realized something that would be easier before I did that. Remember that when you multiply two complex numbers, if you multiply a complex number times its conjugate, you get a real number. So I just realized it would be simpler. I'd have a simpler expression to evaluate if I went ahead and multiplied that complex number times its conjugate. Watch what happens. That x times x is x squared. I have a positive 3i times x and a negative 3i times x. That's 0. And then last I have a negative 9i squared. But you know from your work with imaginary numbers that I squared is just -1. Then that factor simplifies to x squared plus 9 times x minus 4. We know that it's the factor x squared plus 9 that if we set it equal to 0 and solved it, we would get imaginary solutions. We'd get the two imaginary solutions, -3i and +3i, that we were originally given as conditions that we needed to satisfy. So before I started trying to find this coefficient a, I just wanted to clean that up a little bit. Now I'm ready to find that coefficient. When x is -1, y is 50. Make sure when you're substituting a negative in place of a variable that's raised to a power, you keep the negative inside parentheses so that it's part of the base. I put -1 in place of both x's. And then I'm going to simplify that right-hand side. This would be 1 plus 9 is 10. This would be 10 times -5 is -50. So the value of a, the coefficient we're looking for, is -1. And the specific function that satisfies all of the original conditions that we were given, substitute that -1 back into this function, and you have -1 times x squared plus 9 times x minus 4. Again, you could take that a little farther and FOIL this out, distribute the -1. That probably is the answer that they're going to have in the back of the book, but I'm fine if you just stop and leave that in factored form. All right. We have two other problems that say find a polynomial with given zeros, but actually we have three. But in these next examples, we're not just looking for a third-degree polynomial. In number 10, we're asked to find a seventh-degree polynomial. A seventh-degree polynomial such that -2 and 2 are both zeros of multiplicity 2, and 0 is a zero of multiplicity 3. And then we have the condition f of -1 is 27. This is where we would go back to our note on multiplicity and understanding what multiplicity means. If we're looking for a seventh degree polynomial, that means that whatever factors I have, their exponents have to add up to 7. And if -2 is a zero of the polynomial, then x plus 2 has to be a factor. And if 2 is a zero of the function, then x minus 2 has to be a factor of the function. And what about 0 is a zero? What factor gives us 0 as a zero of the function? Well, that's when we have a factor of plain x, or we could write it x minus 0. There's just no need to do that. Now, right now, I have a function with zeros, 0, -2, and 2. But if I multiplied that all out, I would have a third-degree polynomial, not a seventh-degree polynomial. So I have to figure out what to do with these multiplicities. -2 and 2 are both zeros of multiplicity 2. What does that mean about these two factors? It means their exponents are 2. Now, -2 is a zero of multiplicity 2. And +2 is a zero of multiplicity 2. How would I satisfy 0 is a zero of multiplicity 3? That just means the exponent of my factor x needs to be 3. Now I have a seventh degree polynomial with the given zeros and the given multiplicities. What I don't yet have is this last condition, f of -1 equals 27. Well, that means I need to solve for the coefficient a, such that if x was -1, y would be 27. Let me go ahead and put 27 in place of f of x and -1 in place of each of those x's. (27) in place of y and -1 in place of each of the 3 x's. Clean up that right-hand side. -1 cubed, still -1. -1 plus 2 is 1. 1 squared is 1. And -1 minus 2 is -3. -3 squared is 9. So 27 equals -9a. That means the coefficient we need is -3. A coefficient of -3 will cause this general polynomial to satisfy this last condition. So the specific polynomial, which is my answer, is the coefficient -3 times the x cubed times the x plus 2 squared times the x minus 2 squared. That has the given zeros with the given multiplicities and also meets the condition f of -1 equals 27. All right. I have 2 more of these. And number 12 says find a 4th degree polynomial whose function is shown in the given figure. Looking at that graph, I can see the x-intercepts or zeros of the function. Looks like the graph crosses the x-axis at 0, at 1, at 2, no, I'm sorry, that's 3, and then at 5. So this function has 4 x-intercepts or 4 real zeros of 0, 1, 3, and 5. That already tells me 4 factors of that function. In order for 0 to be a 0 of the function, I need the x-intercept, or I need the factor of a plain old x. In order for 1 to be a 0 of the function, I need the factor x minus 1. In order for 3 to be a 0 of the function, I need the factor x minus 3. And in order for 5 to be a 0 of the function, I need the factor x minus 5. Now notice, if I multiplied that all out, I would have a 4th degree function, which is what I'm looking for, 4th degree polynomial. One other thing I can notice is the graph crossed the x-axis at each one of those intercepts. It didn't do a U-turn at any intercept. That means all of these factors are of odd multiplicity. Actually, to be a 4th degree polynomial, they would each be raised to the 1st power to have odd multiplicity, but a 4th degree polynomial. So the only other bit of information that I need from the graph, the other condition that I need to satisfy, is that f of -1 has to equal 4, and I can use that to find the coefficient excuse me, of the polynomial that I'm looking for, just like I have on the other problems. If I let all those x's be -1, then y will be 4. And on the right hand side, when I clean that up, I'm going to have -1, a times -1 times -2 times -4 times -6. And when I multiply 4 negatives, I get a positive. So 1 times 2 is 2, 2 times 4 is 8, 8 times 6 is 48. And if 4 equals 48a, and I divide both sides by 48 and reduce that, the coefficient that I need to satisfy this last condition is 1/12. So the function that I'm looking for is 1/12 times these other factors, x times x minus 1 times x minus 3 times x minus 5. All right. The only reason I want to do one more of these is an interesting twist on number 14. Again, we're given the graph, and from the graph we can see the two x-intercepts are 2 and 4, and that means the function that we're looking for has to have the factors x minus 2 and x minus 4. However, this says find a polynomial function of degree 3. Well, right now, if I multiply these two factors, I'm going to have a quadratic function, a second degree function. And I know with even degree functions, both ends of the graph have to be going the same direction. So I know I haven't satisfied that condition yet. One of these factors needs to be squared if I'm going to get a third degree polynomial. How do I decide which factor needs to be squared? We'll look at the graph at each of the intercepts. At the x-intercept 2, the graph does a U-turn. That means the factor x minus 2 has to have even multiplicity. That means its exponent needs to be 2. The x-intercept 4, at that point the graph crosses the x-axis. That tells me that at 4 the function had odd multiplicity, and so its exponent is 1. And now I have a third degree polynomial. I only have to find the coefficient that will cause this graph to meet the other condition. That other condition is f of 1. When I let x be 1, y is supposed to be -3. I'm actually not going to finish this problem because we've done several problems now where we can find the coefficient that satisfies this last condition. Just let y be -3 when both of those x's are 1. Solve for the coefficient a, and then write the specific function that you're looking for. I think you have enough examples of that. And there are actually two other things in 3.3 that I want to mention. The second thing in the notes is finding zeros of a polynomial function. You need to look at this theorem on the exact number of zeros of a polynomial. If f of x is a polynomial of any degree n is greater than 0, and if a zero of multiplicity m is counted m times, then the function f of x has precisely n zeros. What that's saying is if you have a 5th degree polynomial, then it's going to have 5 zeros. Now, there aren't any restrictions on those zeros. They may not all be real zeros. They may not all be x-intercepts. If some of the zeros turn out to be imaginary numbers, then they're not going to be x-intercepts. But if you have an nth degree polynomial, it's going to have n zeros as long as you counted the zeros with multiplicity higher than 1, you count them separately. In other words, this number 10 was a 7th degree polynomial. If you count the 0, 0 3 times, and the 0, negative 2 times, and the 0, positive 2 times, then you could say, yes, that function has 7 zeros. Some of them are repeated, all of them are real, but there are 7 zeros. And back on number 6, we had a 3rd degree polynomial. Here's the 3rd degree polynomial we ended up with. It did have 3 zeros. 2 of them were imaginary, the positive 3i and the negative 3i. Only 1 was real. So that graph only had 1 x-intercept because 2 of its zeros were imaginary, but it did have 3 zeros. So that's what the theorem on the exact number of zeros of a polynomial is saying. Let's look at some examples. And these just say, find the zeros of the function and state the multiplicity of each zero. Number 16, I'm not even going to write this one down because it's easy to look at that and see the zeros of the polynomial. If I set each of those factors equal to 0, I would get 0 is a 0 of multiplicity 1 because the exponent of that factor is 1. If I set x plus 1 equal to 0, I'd get the 0, negative 1, and its multiplicity is 4 because that's the exponent of that factor. And then if I set 3x minus 7 equal to 0, I would get the 0, 7/3, and it is of multiplicity 2. So if I multiplied that all out, I'd get a 7th degree polynomial because the 1 plus this 4 plus that 2 gives me 7. So I have a 7th degree polynomial. It has 7 zeros if you count 0 as 1 0, negative 1 4 times, and then positive 7/3 2 times. What about number 18? I think I want to write that one down. If you multiplied 4x squared minus 5 times 4x squared minus 5, multiplied it by itself, which is what squaring it means, you'd have a 4th degree polynomial. So when we find the zeros, we should have 4 zeros, even though some of them may be repeated, and some of them may be real, and some of them may be imaginary. Let's see. The zeros, we can get them by setting that factor equal to 0, solving the quadratic equation, adding 5 to both sides and dividing by 4. When you take the square root of both sides, don't forget your plus or minus. And then if you divided that radical up into the numerator and denominator, there's not much you can do with square root of 5, but you can say square root of 4 is just 2. So the two distinct zeros are positive square root of 5 over 2 and negative square root of 5 over 2, but the multiplicity of each of those zeros is 2 because the exponent of that factor is 2. So if we have 2 positive square root of 5 over 2's and 2 negative square root of 5 over 2's, then we've accounted for all 4 zeros of that function. One more of these. Number 20. Again, we're just looking for the zeros and the multiplicity of each zero. And I think this will factor. It's a 4th degree polynomial, but there are factors of 100 that have a difference of 21. So I'm just going to try to factor that. The x to the 4th has to be x squared times x squared. The factors of 100 that have a difference of 21 are 25 and 4. And in order to obtain a positive 21 in the middle, I need that 25 to be positive and the 4 to be negative. Always check your factoring, multiply that back together real quickly to make sure it gives you what you started with, and then see if you can factor further. You can't factor the x squared plus 25 any further because it's the sum of 2 squares. But the x squared minus 4 factors into x plus 2, x minus 2. And so we can get the zeros of this function by setting each factor equal to 0. And I can see that I'm only going to have 2 real zeros, or 2 x-intercepts, -2 and +2. This first factor will give me imaginary zeros, plus or minus 5i. So once again, it was a 4th degree polynomial, and it has 4 zeros, each of multiplicity 1, because in my final factored form, the exponent of each of those factors was 1. And 2 of my zeros are real numbers, 2 of my zeros are imaginary numbers. All right. The last thing in 3.3 is factoring a polynomial function. Number 24 having a little bit of trouble with my camera wires here. Number 24 says, show that the number is a 0 of the function. We're given some number. In number 24, we're given the number 4. Show that it's a 0 of the function. We have to think back to how we did that in 3.2. In 3.2, we had a theorem that says if 4 is a 0 of the function, then when we do synthetic division, the remainder should give us 0. And here we're told that not only is 4 a zero of the function, but it's a zero of multiplicity 2. We're going to show that 4 is a zero of multiplicity 2, and then use that to factor this 4th degree polynomial that we could not have factored previously into a product of linear factors. So number 24. Again, if 4 is a zero of the function, that means if we do synthetic division with 4 in the box, we should get 0 remainder. Now, before I write down the coefficients for synthetic division, I'm going to check to make sure, or to see if I'm missing any terms. I have my 4th degree term, my 3rd degree term, my 2nd degree term, but I'm missing a 1st degree term. I have to be aware of that and put in a 0x to the first for that missing term, and then I have my constant negative 32. So the coefficients of this polynomial are 1, negative 9, 22, 0, and negative 32. Now I'm going to do synthetic division and see if I get a 0 remainder like this problem is saying that I should. Bring that first coefficient straight down, then start the process of multiplying, add. 4 times 1 is 4, add. 4 times negative 5 is negative 20, add. 4 times 2 is 8, add. 4 times 8 is 32, add. The fact that I got 0 remainder does mean that 4 is a zero of that function, and it also lets me simplify or partially factor that function. If 4 is a zero, then x minus 4 is a factor, and my 3rd degree factor will have these coefficients. 1 is the coefficient of x cubed, negative 5 is the coefficient of x squared, 2 is the coefficient of x, and 8 is my constant. So knowing the first factor of this polynomial has allowed me to, or first zero of this polynomial has allowed me to factor this function into a linear factor times a cubic factor. And I still couldn't factor that any further using the skills that I learned in Algebra 1, for example. It won't factor by grouping. So I have to use the fact that the original problem told me 4 is a zero of multiplicity 2. That means if I do synthetic division with 4 in the box again, but now I use this factor, the 3rd degree factor, I should still get a 0 remainder. Let's see if we do. Something just happened. There. Sure enough, I got 0 remainder again. So my function can not only be factored into this x minus 4, but I'd have another factor x minus 4. and then the quadratic factor, x squared minus x minus 2, which has these coefficients, 1, -1, -2. And then finally, I have a quadratic function that I can factor with my traditional methods. Just want to double check my factoring, multiply that back together, make sure it gives me what I started with. And now you can see that knowing that 0 was a 0 of this function and it had multiplicity 2 allowed me to factor something that I could not have factored before into 4 linear factors. And of course you could write this as x minus 4 squared, that doesn't matter, but I can see all 4 zeros of that function are positive 4 of multiplicity 2, and then -1 and positive 2. All right, that's all that's in section 3.3. The one other skill that we have left to learn is, what if I had not been given that 4 was a 0 of multiplicity 2? What if I was just given that original equation or that original function? I was told to find the zeros, but I wasn't giving anything to start with. How would I have found those first 2 zeros that would have let me factor this 4th degree polynomial into this product of linear factors? That's what's coming up in 3.4. And then the homework, I've retyped it on the notes that I sent you, because my old notes had the 12th edition page numbers and 12th edition homework problems. I've corrected this for the 11th version of the text. These are the correct page numbers. And 3.2, which I sent you yesterday, it did have 5 problems, but these last 3 problems had different numbers in the 12th edition, so I've corrected that. If you've already done the homework that I gave you for 3.2 yesterday, don't redo anything. But if you haven't done it, do these last 3 problems rather than the 3 problems that were on the handout that I sent yesterday. 3.3 and 3.4 homework, this is correct for the 11th edition. There's one more video you need to watch before you do section 3.4, and then you can give all this 3 sections of homework to me next time I see you. Have a good day.